Welcome back for our next lesson in the Chemical Basics unit. The second video here is on atomic mass. We have two learning targets in this video. We want to be able to define and calculate atomic mass and use atomic mass to determine the percent abundance of isotopes. So first of all, a little background on mass and atoms. One thing we need to consider is the mass unit that we would use to measure the mass of individual atoms. We know atoms are really small. The question we want to kind of ask is how small and what kind of unit would we need? Well, the unit that we use to measure individual atoms is known as the atomic mass unit. Atomic mass unit. Symbolized by the abbreviation AMU. Just to give you an idea of how small the atomic mass unit is, 1 AMU is equal to roughly 1.66 times 10 to the negative 24th grams. So it's a really small unit of mass. Just like any other unit, there needs to be some sort of definition or standard by which it's determined. Well, what chemists have done over the years is they have picked an atom, a particular isotope of a particular element, in order to determine or define what an AMU is. The definition of an AMU is this: one atom of carbon-12. One atom of carbon-12 has the exact mass of 12 atomic mass units. So that is how the AMU is defined. If you have a single atom of carbon-12, recall the 12 there is the mass number. So we're talking about a carbon atom with 6 protons and 6 neutrons. Well, every carbon atom has 6 protons. This one has 6 neutrons in it. That mass of that atom is exactly 12 AMUs. The mass of every other isotope of every other element is determined relative to this carbon-12 atom. So that's how we determine what the mass of atoms are, at least relative to the carbon-12 atom we do. Now what we want to do in this video is talk about atomic mass and what atomic mass is. Atomic mass is the weighted average mass of all stable isotopes of an element. The weighted average mass of all stable isotopes of an element. The idea of a weighted average might be familiar to you. It's a situation where not everything that goes into the average counts equally. Some of you might have classes where your grade is calculated based on a weighted scale. In fact, the first example I'm going to show you here in a second deals with calculation of a grade. In other words, what this means that it's weighted is the abundance of each isotope affects the atomic mass. Abundance of isotopes affect the mass. Affect the atomic mass. So an element might have 2 or 3 or 5 or 7 different stable isotopes, but those isotopes don't all occur equally. There's not the same number of each atom of each isotope. Because there's different numbers, we have to account for the fact that there might be a lot more of one isotope than another. So that being said, let's jump down and look at the example problems here. Just take a look at the first one here. And this is the example I was telling you about with calculation of a grade. You're told your math teacher uses a weighted grading system as follows. Exams count for 70% of your grade and homework 30%. Below are your scores in each of those areas. Determine your grade in this class. You see your exam scores total to an 82 and your homework scores total to a 94. Well, if we were just to find the average of those two, if we were just to add the two up, 82 plus 94 divided by 2, that would give you an average of 88. That would be the average. The problem is we're not accounting for the fact that 70% of your grade comes from the exams and 30% from the homework. Okay, so this doesn't really work in this situation. We have to have a different way to find the average. Here's how we do that. We are going to take the percent of your grade that counts for the exam, 70%, and turn that into a decimal. So 70% That would be 0.70 in decimal form. And we're going to multiply that percentage by your score, which is an 82. And then we're going to add that same product from the homework. The homework counts for 30%. So in decimal form, that's 0.30 times your homework scores of 94. And that will give us the weighted average for your math grade. Now when you plug this in your calculator, in this case we don't really need to worry too much about sig figs, as these here would be counted, not measured. But say we did have sig figs. What we'd want to do is we'd want to do the multiplications first, so 0.7 times 82. And the 0.70 and the 82 would generally both be 2 sig figs, even though these aren't really measured. Let's say they are. So I'd have to round my answer here to a 57. So that would be 57 plus 0.3 times 94. That would have to round to a 28. And then I just add those two together. So 57 plus 28 gives us an 85. And that would be our final score in math. Now ask yourself, is this closer to the exam scores or the homework scores? Obviously this final score is closer to the exam scores. Why is that? Well, simply because the exams count for more of the grade. The exams count for 70% of the grade. The homework only counts for 30%. So that final score will be closer to the exam scores. The atomic mass of elements works the same way. It will always be weighted closer to the isotope that there's more of. Whatever the mass of an isotope is that's more abundant, the atomic mass will be closer to that simply because there's more of those atoms. So let's take a look at the calculation of an actual atomic mass. This is on the second page here. Alright, this is example problem number 2. We're told chlorine has 2 naturally occurring isotopes, chlorine-35 and chlorine-37. And it asks us to use the data below on the 2 isotopes to determine the atomic mass of chlorine. So here are 2 isotopes, chlorine-35 and chlorine-37. And we're given the actual mass of these isotopes. The actual mass of chlorine-35 is 34.969 AMUs, 37 is 36.966 AMUs, and we're given the percent abundance of each. So of all the chlorine atoms that are in this universe, 75.78% of them are chlorine, 24.22% of them are chlorine-37. Alright, so to find the atomic mass, I'm going to take the percent abundance in decimal form, so 0.7578, and multiply that by the actual mass of 34.969 AMUs. And I will add to that the same thing for the other isotope, 0.2422 times 36.966 AMUs. Alright, again, when you do this, plug in your calculator, you do want to do the individual multiplications first, because the sig figs you need to round there first and then do the addition. So I have 0.7578 times 34.969. And you can see that gives me 26.50. Need to round to 4 sig figs because that's all the percentage has. AMUs. Plus 0.2422 times 36.969. Excuse me, 966. Try that again. That is, and this is 4 sig figs as well. 8.953. 953 AMUs. Now remember, when we add these together, I have to look at decimal places. This first value now only goes to the hundredths place. The second one goes to the thousandths. I'm going to need to round my answer to that hundredths place. So 26.50 plus 8.953. My calculator tells me 35.453 AMUs, but based on my significant figures here, I need to just round this to 35.45 AMUs. That would be the atomic mass of chlorine. Ask yourself, why is it closer to 35 than 37? Well, that's because there's about 3 times as much chlorine-35 as there is chlorine-37. So that atomic mass will get shifted towards the more abundant isotope. Since this is a real element, obviously chlorine is a real element, a great way to check yourself is to check the atomic mass of chlorine on the periodic table. So if you take a periodic table and take a look at it, find chlorine on there. I'll zoom in here a little bit for you. And here's chlorine. Its atomic mass is listed as 35.45. So we probably did it correctly. At least a pretty good shot that we did. Alright, before we go to this next example problem, I do want to go back and jot down a couple other quick things under the key ideas and definitions. You'll notice on that last example that the actual mass of those isotopes, the actual masses are close to mass numbers, but they aren't exactly the mass numbers. You might be wondering why that is. Let me just flip back here to that last example. If I look at the actual masses, a chlorine-35 atom has a mass of just under 35 AMUs. Chlorine-37 has a mass of just under 37 AMUs. You might be thinking there's probably a reason why that is, and there is. There certainly is a reason why that is. It's because a proton and a neutron are both approximately 1 AMU. Okay, they're actually both slightly heavier than 1 AMU. So when we talk about a mass number, remember those are protons plus neutrons. Let's jot that down here again. Protons plus neutrons. So that mass number is the number of protons plus neutrons. So when we say chlorine-35, there are a total of 35 protons and neutrons in there. So we would expect that the mass would be about 35. One thing you might have picked up on, though, was I said that they are both slightly more than 1 AMU, but when you look at the actual mass, it's actually slightly less than 35. You would expect them to be more, because if all these are slightly more than 1 AMU, then it should add up to more than 35. Well, the reason why it's a little short of what you would expect is there's always a mass deficit. A mass deficit occurs, I'm not convinced I spelled deficit right, when nuclei are formed. In other words, whenever a nucleus comes together, part of the mass of those protons and neutrons get lost to form energy. This comes from Einstein's famous E equals mc squared equation. This really isn't anything you need to be too familiar with. I think it's pretty interesting, though, so I thought I'd throw it on here. So the reason why those actual masses are slightly short of the mass numbers and not a little more, as you might expect, is because of that mass deficit. Alright, so let's take a look at that last example problem. Alright, so we are told the atomic mass of boron is 10.811 AMUs. Boron has two naturally occurring isotopes, boron 10 and boron 11, with masses of 10.013 AMUs and 11.009 AMUs, respectively. Determine the percent abundance of each isotope. Alright, so here it's backwards from what we've already done. Before we found the atomic mass given the abundances and actual masses. Here we're given the masses of each isotope and the atomic mass. We're asked to find the abundances. Well, here's what we know. We know that if we take the mass of boron 10, I'll write it like this. If I take the mass of boron 10 and I multiply that by the abundance of boron 10, left out the B, and I add to that the same thing for 11, the mass of boron 11 times the abundance of boron 11, that's going to equal the atomic mass. That's how we calculate atomic mass, which we're told is 10.811 AMUs. Well, we're also given the masses of these things. We're told boron 10 has a mass of 10.013 AMUs. And I'm going to substitute in an X for the abundance of boron 10. Plus, I know the mass of boron 11 is 11.009 AMUs. And I'm going to substitute in a Y for the abundance of boron 11. That's going to equal 10.811 AMUs. So we can see here that we have two variables that we need to find, X and Y. Well, you learn in algebra that if you have two variables that you need to find, you need two equations. Well, we have one equation here, the one we just wrote. The second equation is the relationship between X and Y. If you think about what X and Y represent, the abundance of the two isotopes, I know that if I add them together, X plus Y would have to equal 1, because they have to add to 100%, or in decimal form 1. So if I substitute this equation in for either X or Y, I could solve this equation for one of them and then get the other. So if I solve this, say, for y, that would be y equals 1 minus x, just substituting or subtracting x over to the other side. I'm going to substitute this value in every time I see y, which happens to just be one place, which is right there. So just rewriting this equation with that substitution, we have 10.013 AMUs times x plus 11.009 AMUs times y, but that is now 1 minus x equals 10.811 AMUs. From here, it's simply the algebra that you guys have learned how to do. I need to solve this for x, so I'm going to distribute my multiplication here. So the left side, the very left side doesn't really change any. That's 10.013 AMUs times x. Now I need to distribute this. I have 11.009 AMUs times 1. Well, that's just 11.009 AMUs. And then 11.009 AMUs times a negative x. Well, that's going to give me minus 11.009 AMUs times x equals 10.811 AMUs. Alright, I've distributed my multiplication. Now I need to add my like terms. I have two terms that include x. So I'm going to add this term. I'm going to put a little bracket on it so you guys can see exactly what I'm saying here. I'm going to add this term and this term. They both have x's. So if I add those together, to show you what I'm plugging in here, that would be 10.013 plus a negative or minus 11.009. That gives me negative 0.996 AMUs. Negative 0.996 AMUs times x. And then I'm also going to add, I'll use a different bracket here, I'll use more of a square bracket. I'm going to add these two terms together. Okay, those don't have the x in them. So I'm going to subtract my 11.009 to the other side to get it on opposite sides. So I'm going to take 10.811 minus 11.009. That gives me negative 0.198 AMUs. At this point, I can simply solve for x. If I divide both sides by a negative 0.996, so I have negative 0.198 divided by my negative 0.996. This gives me a value for x. And notice this is sig figs. I have 3 sig figs here in both those measurements I have left. That gives me 0.199 for x. Okay, so I have x now. If I think about what I said at the beginning, I know that y equals 1 minus x. So y equals 1 minus x, which is equal to 1 minus 0.199. So y is equal to 2.801. That's what that is. Now we're not quite done yet. We still need to actually get the abundances here. I need to go back and look. I can see I substituted x for the abundance of boron 10. So the boron 10 abundance is going to equal to 19.9%, or you could write 0.199. That would be okay as well. And the abundance of boron 11, I can see I substituted y in for the abundance of boron 11, is equal to 80.1%. And we're done. The key on problems like this here is simply doing the algebra. Okay, you guys have learned the algebra in algebra class. It's just a matter of applying it. Alright, there is one practice problem here, so I would encourage you to stop the video at this point, try this yourself, and then see if you did it correctly. Alright, we're asked to determine the atomic mass of the fictitious element iowanium using the isotopic data below. So here we have 3 isotopes. If I have 3 isotopes, it's no different than doing it with 2 isotopes. I still need to multiply the abundance of each isotope. So in decimal form, so it would be 0.29203 for this first one, times its mass, in this case 312.988 AMUs. And I'm going to just sum each of those products for each isotope. So just completing this here, times 317.971 AMUs plus 0.51595 times 320.991 AMUs. Alright, so again, when you plug this in the calculator, do the multiplication first. For the first one, looks like we get 5 sig figs. I get 91.402 AMUs to 5 sig figs. Looks like each of these we're going to get 5 sig figs. For the second one, I get 61.057 AMUs. For the third one, I get 165.62 AMUs. When we add these together, remember we're looking at decimal places. This last value now would limit us because it only goes to the hundreds place. So when you add these together, 91.402 plus 61.057 plus 165.62, your calculator is going to tell you 318.079 AMUs, but you need to round that to the hundreds place here, so that becomes 318.08 AMUs. And there's our answer.